We've talked about the shapes of distributions and how to describe them. One of the most important distributions we're going to be dealing with in this course and throughout the rest of the term is a shape that has a unimodal peak and is symmetrical around the mean. This is referred to as a normal curve. The normal curve has one peak and is symmetrical around the mean. It so happens that the z distribution that we just talked about has a normal curve. We'll revisit that in a couple chapters to explain why it's a normal curve, even if our data isn't a normal curve. But the z-transform does follow a normal. This is incredibly useful because it turns out that we can calculate the amount of our data that falls between the standard deviations on a normal curve. Remember, the z-score is the number of standard deviations away from the mean. So if we were to look at one standard deviation either above or below the mean, right, one standard deviation in the positive direction, one standard deviation in the negative direction, about 68% of our data is going to fall within that range. If we were to look at positive 2 and negative 2, right, so plus or minus 2 standard deviations, 96% of our data is going to fall within 2 standard deviations of the mean. One of the questions I have for you is why on a given data set all of our data isn't the same, right? Well, it's because there is random fluctuation, right? There's random chance. On any given day, any given person, any given circumstance, our scores are going to fluctuate and change. The normal curve represents the distribution of our data, assuming random chance. Right? So sometimes our data is going to be larger than the mean. Sometimes our data is going to be smaller than the mean. It's going to depend on all of these random fluctuations, all of these random things that we can't control. But 96% of our data is going to be within 2 standard deviations. Right? The further away we get from the mean, the less and less likely that data is to appear. So a very small percentage of our data is going to be 3 or 4 standard deviations away. And this becomes very important when we start talking about things like, for example, is there a rise in the number of COVID cases in a given state? Let's take a look at New Mexico. So one of the reasons why they are saying we've seen a rise in the number of COVID cases in New Mexico is this data that's out here at 319, 220 new cases a day, right? This is out here. It is part of the right skew, and it does seem as if it indicates an increase, right? Why are we saying it's an increase? We're saying it's because it's so far away from the mean, right? It's multiple standard deviations away from the mean. It seems highly unlikely, right? So notice what the question is here, and this is very important to capture the reasoning of the course going forward. So listen carefully to the reasoning here, right? What we're saying is that there is a chance that we could get 319 new cases of COVID without there being a reason for it by random chance alone. Right? The number of new cases we get a day is affected by random chance, and it is possible that due to just a conflux of a whole bunch of random pieces, we just happen to get a very large score that day, a very large number of cases that day. But the chances of it being due to random chance alone become smaller and smaller the further away we get from the mean, the less and less likely it is. That's what the z-score tells us. The z-score tells us how many standard deviations away from the mean it is, and thus how likely it is to appear by random chance alone. And if we decide that the chance of it appearing through random chance alone is just too small, then we need another explanation for it, like there has been an increase in the number of cases. So let's come down here to where we see the actual bump in the number of cases. So 319, 213, 224, these were the days that saw our big bump. If we come over and we look at the z-scores, we can see about 1.9, 1.7, and 3.5. Right? So the 224 and 213 are within 2 standard deviations. Right? So we would expect to see that 96% of our data falls within that distribution. But boy, that 319 is 3.5 standard deviations away. That seems incredibly unlikely. But boy, it sure would be helpful if we could know exactly what percent chance that 3.5 is. Well, we can actually calculate this. We can calculate the percent chance given a z-score using some calculus. The good news is we don't have to do that. That has been done for us and is in the appendix of your textbook in the first table we are going to use called the z-table. Let's take a look at that. I'm in the textbook now. We are in the appendix, table A1, the very first page of the appendix, and this is the z-score appendix, and it's going to be incredibly useful for us as we try to interpret what our z-scores mean. So this first column is the actual z-score. The second column is the percentage between the mean and that z-score. We're not really going to be using that very often. The main thing we're interested in is the percent and tail. The percent and tail tells us what percent of our data is at that z-score or greater. And this tells us to some degree how likely our data is. For example, if we have a z-score of 0, right, half of our data, right, from the mean on up would be bigger than that z-score. So let's take a look at our 3.5 z-score we got for that one-day New Mexico testing. So we scroll all the way down here. We're looking for the 3.5. There it is. So 3.5 z-score. And what we find is only 0.02% of the data would be expected to be at 3.5 standard deviations or greater due to random chance. So what this is saying is that there is only a 0.02% chance that we would get that number of cases by chance alone. 0.02% chance. And that's a very, very small percentage. And leads most people to believe that that did not happen by random chance alone, and that was driven by something else, that there's something new about that data point that suggests that the number of cases is increasing.